Particularly, this is on the solar irrigation and its implications on the groundwater use. Yesterday, also in one of the sessions we were talking about. And the basic idea behind this was, as we have been discussing yesterday, is that now with the fact that our earlier evidence shows that if the electricity is free, energy is free, people tend to pump more groundwater, extract more groundwater. That's kind of the thinking. And now with the solar irrigation becoming increasingly common, if it is so, and if it goes at that pace and if with a zero marginal cost, then perhaps it's a thinking that the farmers will have a tendency to suck more water. And so that's the kind of the premise which there are kind of the thinking in the people's mind. And so this particular session is basically devoted to some of the kind of the experimental evidences or kind of the things. And also then it will be followed by a panel discussion. Then that panel discussion theme is more on the groundwater modeling to try and answer that kind of a question. So that's so there are two parts to this particular session. There are the first three presentations are there, and followed by the panel discussion. And and you'll see here that there's a presentation from Africa. My colleague from Africa is there, Manuel, and also two of my colleagues from IWMI are there. And then of course we'll have a very useful panel discussion. And when I look at the list of the panelists, I mean, great panelists. So I do not know what question I should be asking them, but any I'll try my level best. So with this, I think then we can start, and I invite Manuel. Manuel, you are there? Yes. For the first presentation, and you have 15 minutes for your presentation. All right? Okay. So please.
I will be wrong.
Okay.
Yeah. You just send me next.
Okay. Good morning, everyone. My name is Manuel Magombeyi. I'm based in the Southern African office in Pretoria at IWMI. I would like to just share with you some of the work that we are doing in terms of solar irrigation, and also how do we make water available in our dry region. So I think just as an introduction, we've been hearing, I think in the previous presentation, that energy consumption, I think in terms of production, and accounts for about 2/3 of the greenhouse gas emissions. And also we understand that about 81% of the global energy mix is still based on fossil fuels, which means if we are to change this scenario, we need to do more in terms of renewable energy. And solar is one of these renewable energy sources that we find to sort of adapt or also mitigate against these greenhouse gas emissions. In many parts of Southern Africa, we have got challenges in terms of the affordable clean energy, which can be a limiting factor in terms of water access by the smallholder farmers, and also reduce production income because of the high energy costs that are related to the fossil fuels. So considering that agriculture consumes about 80% of water, solar has the potential actually to provide sustainable energy for pumping about more than 95% in agriculture compared to other energy sources. So the possible benefits, I think Alok has highlighted that there has to be a trade-off to say, when we provide this clean energy or this free energy, what will be the implications in terms of water abstraction, in terms of groundwater? So there has to be trade-offs that we have to make there. In terms of addressing this challenge, we have addressed through bundling technologies, the Bunkro technology, which ensures that we have got more water available to the farmers in terms of artificial recharge, and also the solar system. But next slide, please. But what we have found is that I think it's very interesting that here in Gujarat, where this bungur technology was first developed to address flooding, where you have got high floods, the water is channeled into a well to recharge during the rain season, and during the dry period, that water is further abstracted for irrigation. And we used a similar technology in the southern region, and you will find that because it's a bit drier, what we have done is we have modified it to harvest water from the catchment around the well that we want to recharge, and then channel it into the bore. So that's very interesting. Next, so just the previous slide. Yeah, previous slide. Yes. So what we have done is there is a lot of training that we have done to the farmers on how to install this bungur technology, how to operate it, and also in conjunction with the solar system. So what is key now is, since it's a demonstration, is to sort of demonstrate whether this system is viable, how does it help farmers in terms of income, in terms of water availability, in terms of changes in water quality, because we are introducing water that is harvested around the catchment into the aquifer. So we need to check those things so that we don't end up having water that will affect our crop production or that will pollute the aquifer. So that's what we have done. And there are several methods that we have used, for instance, to check the recharge, the chlorine mass balance, and the isotope, stable isotope method, which enables us to quantify recently recharged water and water that was in the well before. And we've done estimation of how much water are we recovering from this well for use by the farmers, and also the energy use estimation. I think with this, we want to sort of, in terms of scaling, what are sort of the guidelines that we can put to guide further development of this technology in the smallholder farmers. Next slide. So in this area, you find, so our study area was in South Africa. It's in Southern Africa. And that side, you have got the, what we call, it's a bigger basin, which is called the Nkomati Usutu Catchment Management Agency. And within this catchment management, and we've got sub-catchments. So it's like a hierarchy in terms of water management in the Southern Africa. So we did a suitability mapping of the bungur and the solar system. And that is the map that you can see on the left-hand side there. And these areas, like as I mentioned, the rainfall is about 400 or less than 500, both of them, which means in terms of flooding, we have got less flooding in this area. So what we have is to just collect water from the catchment around and recharge it. Right, next slide. So what is coming out from this pilot study is that from the analysis that we have done, we have found that about 11% of the area that is analyzed shows high suitability for this bundled technology, the bungur technology combined with the solar technology. And about 13% is, so 11% showing very high suitability, 13% high suitability, and the rest of the area is a moderate. So what we have realized is that there is potential in these areas for this suitable technology to help several farmers to make water available and the use of clean energy. When we analyzed the changes in water quality, we did the physical, we did the chemical, we also did the isotopes. We managed to analyze, we managed to get that there is no change in water quality that has been as a result of this recharge. And also the sodium absorption ratio, which is required when you want to analyze water for irrigation, it was within or below the standards. And the recovery efficiency in our first year, I think for one of the sites, it ranged from, for the two sites, it ranged from 6% to 18%. But we understand this with technology, with time, the recharge is going to increase as we harvest more water into the area. And also, yeah, I think that's what is key. And the next slide, please. These are just some of the photos that we took in the field, which showing the different solar systems that we installed. And this is one of the areas where the farmer is doing both crop production, and this is macadamia nursery, which is a very high value tree or crop. And in other areas, we have seen change of from hand pumps to solar in other areas. And here we see the normal diesel pumps that the farmers have been using. Next slide. So the energy costs from the fuel pump and the grid connected pump, I think made up about 9 to 42% of the production cost. So you see how what impact you have if you reduce this cost to when you use solar. It means you increase the income that the farmers are getting. And also, especially now that the fuel is very expensive to use diesel pumps, solar is becoming very attractive to these farmers. We also have here the reduction in energy cost resulted in about 29 to 84% increase in your gross margin of the farm when we compare the grid connected pump and the off grid. And the use of water, we have got about 5,800 to 9,200 cubic meters per hectare. And this gave us a yield of about 22 to 45 tons for the cabbage crop that we monitored. Just to have a clear on the productivity, how much is this water going to produce? We have got about 3.5 to 4.9 kgs per cubic meter that is produced. And of course, the estimation of the carbon emissions reduction, we have got about 35 to 40 tons, where we have got the solar versus the fuel, and also where we have got the grid connected pump versus the solar, we have got about 10 to 11 tons reduction. Next slide. So what is the regional perspective? What we are looking at, I think what is interesting, you have got a lot of countries, Bangladesh, Nepal, India, that you are sort of trying to understand how does solar perform in all these different regions. And we are following up in terms of our Southern African region, whereby we have got projects that are starting now, for example, in Tanzania, Zambia, and Zimbabwe, where we have got the accelerating impacts for CGI climate research in Africa, where IWMI is heading some of this research. We are installing these solar pumps with smallholder farmers. We have got another project in Zambia, Zimbabwe, DRC, and South Africa, where we have got the We for Food that is supported by the USAID. Also, solar system installation and monitoring are being done there. So we need to sort of bring together these experiences that we are starting to have in the Southern African region. Of course, South Africa, Benin, and Botswana. So those are some of the issues that we would like to understand at a regional level: water use, impacts of groundwater levels and quality. What is the productivity compared to what the farmers are using? What are the reductions in carbon emissions? And also do some water accounting. What is the impact of this when we look at a basin scale? Let's say we have got 100 farmers that are using solar. What is the impact at a bigger scale? What is the impact in terms of water balance? Next slide, please. So we have
2 more minutes.
Yes, we have some opportunities and barriers that we understand, so that we set to understand in terms of how to upscale this technology. And those are shown here in terms of the barriers, the biophysical, of course, the hydrogeological characteristics, the technical. I think some of these presentations highlighted yesterday, the quality of the solar products, where we have to have good quality so that we don't have frequent breakdowns. The installers, they have to be certified so that we have got good workmanship and avoid these frequent breakdowns. Of course, markets and of course the financial systems, they have to have somewhere to sell. so that the system becomes viable, the more business models becomes viable, so that they get income and be able to repay. And of course, the policy, I won't run much into it. But what is the opportunities that we've seen, I think it's job creation in terms of youth training. I think that's one I can highlight, farmer and youth training in terms of maintenance of this technology. Those are some of the key issues that we will look at next. Right, I think the key messages, I think I've given you all those, whereby we understand that the conjunctive use of this surface and groundwater would enable more water available for these smallholder farmers. We've got reduction in costs, we've got reduction in labor, we've got improved crop yield, income and livelihoods, or of course, the reduced carbon emissions. And the key issue, I think now is to move forward and keep on exploring this energy food nexus with the solar technology, which helps us in mitigating against climate change. Next slide. So those are some of the policy implications. I think this is my last slide. Just, I think, to note is the partnership, I think, for delivery and sustainability. I think we have had several of these partnerships in the previous presentations that are hinged on subsidies, which is quite different from our Southern Africa because we don't have these subsidies. So it's something that is key to note as we go on with the discussion. I think I would stop here. Thank you.
All right, so thank you. Thank you. I think as you all know that we are running short of time already. So if I can allow maybe one question, any burning question, if anybody has, otherwise maybe towards the end we will see. Yes, Nitin.
Thank you so much for the interesting presentation. I mean, your last statement, I mean, actually, like they provoked me to ask this. So you mentioned that there are no subsidies available for the for the system, for the system.
Yes, in those countries it is not.
Yeah.
That's why India is a subsidy driven, that's a demand driven.
Right, exactly. So, but I want to know, because given the cost of installations, that is there. So how it is being sustained, such adoption of such systems, solar-based irrigation systems?
Yeah, just briefly, maybe we can talk more. We have got some models that are coming up in terms of the pay-as-you-go system, whereby we have got some companies, yes, some companies that are coming up to give the solar system or install the solar system to the farmers, and then they will pay after every harvest or after every month. So that's how the system.
So it's a private kind of finance.
It's use and pay. They go and then
the interest rates might be very high in that case.
It's a prepaid charge.
Yeah, prepaid card system is there. All right, so thank you very much, and we'll see if there are. So the next I invite Faiz, and he represents IWMI, and he is working on the solar project. So, and the Faiz will be talking about some of the works which we have been doing in Gujarat on the sky farm.
Okay, hi. So good morning. It was trying. Yeah. Okay, so good morning, everyone. So this is the work we are doing in Gujarat with Indram Sundar is there, might you see with me under the solar project to again assess how upscaling solar, whether solar farmers are pumping more than the non-solar farmers. So that was the basic question, because that was one of the main concerns the people had, like if you put solar, and the reason it derives from is the situation that we have seen in India, is that a lot of electric pumps largely subsidized in Northwest and Southern Peninsula has led to this groundwater depletion. And one of the reasons we say that the cost of pumping, the marginal cost is almost nil. So farmers don't efficiently use water, and this has led to pumping. And so the case is, in case of solar, if the same model is replicated again, will this lead to the same situation across other places if the solar is being upscaled? So that was the main question, whether solar farmers are pumping more. Next, click. Just click, yeah. So that's this. Okay, so again, yeah, we've already talked about the boon or bane. There are other parts other than groundwater. So groundwater is just component of this solar. They're concerned about, there are topics about mitigation, farmers' income,
Enjoy.
Farmers' income, climate change mitigation. So the energy sector, implications for utilities. So those are all factors. So groundwater is not the only factor. Okay. I'll be in the line of sight somewhere. Okay. So, but this presentation we talked about this risk of groundwater depletion, and where we are talking about it under the solar project, as Aditya, I think all of you must be knowing by then, we are working across 4 countries. So we are looking at all these 4 countries, how the solar is playing, especially in Gujarat and Bangladesh, where the places where the solar is taking place are the places where there is already intensely irrigated areas. So we are not having off-grid solar, making rain-fed farmers irrigated. These are already irrigated farmers, and we are transiting them from electricity or diesel to solar. And this scheme, in the morning, Mr. Vohra talked about, this is the scheme we are looking at. This scheme, in a way, design is that if we incentivize farmers to export some of the energy they are producing, so we give them the option other than just pumping, this might lead to, this might be a solution for this threat we have that free power, farmers will keep on pumping more. So what we went on to assess is whether this scheme, where we're giving farmers around 7 rupees per unit to export power out, whether this scheme has led, what are the implications of this result of this scheme on this pumping behavior of solar farmers? And where we are doing this thing, we selected 2 areas, 2 districts, one in Anand, the center nearby, one is Botad in the Saurashtra area. 4 different feeders were selected. One is a solar feeder, another is a non-solar feeder. Why Anand? Anand has highly productive alluvial aquifers, high cropping intensity of around 250%. People are doing paddy here, 10 to 20 HP pumps. Whereas in Botad is hard rock aquifers, shallow aquifers, water goes, there's hardly any water post January, February season, low HP pump, 3 to 7.5 HP pumps. So these are the 2 places we are assessing how solar has played in terms of farmer pumping behavior. And the way we went around is that, of course, there are thousands of millions of pumps, thousands of pumps. We can't monitor everyone. So the way, but the good thing that Gujarat, under sky, but also non-skies, everyone is metered. So we have the energy data available there. So the way we went is around, we did sensor selection. The basic methodology is that if we can derive a relationship between how much energy they are using and how much volume of water they are pumping out, maybe we can utilize the energy data that is already available with the utilities to derive this for the larger set of farmers. So that was the basic methodology that we have used over here. And that, whatever the relationship come out, we can take it pre-sky, but we can also project it for the future with groundwater modeling part. So we went around selecting farmers, around 160 farmers were selected, instrumenting them with instrumented flow meters across these farmer locations, R meters. So this is some of the data that we have collected. We did census of around 400 farmers, 160 were selected for monitoring. We selected 30 farmers for installations. We have been regularly going back to those farmers again to collect their cropping pattern, to collect their pump flow data, the energy use data for the last, I think, 1.5 years now. Before going to the results, so these are some of the basic things we expect, that as the HP of the pump increase, the energy use will increase. Of course, that's clearly visible. 20 HP pump use is around 20 units of electricity every year, where 3 HP pump use is only 5. But the same thing we don't observe in the flow rates. So this is where this contrasting hydrology becomes quite apparent. So these are productive alluvial aquifers, all pumping around 100 cubic meter per hour of water. And it doesn't increases with 10 HP pump to 15 to 20. So that tells you the other factors. It's just not the HP of the pump. Same is the thing in the Botad. Limited aquifer, the flow rate are 30 to 40. Again, doesn't necessarily increases with HP of the pump. Other factors playing out there. And the implication of this is in how much cubic meter of water they are pumping per unit of electricity use becomes apparent here. For example, if 20 HP is using the more electricity but pumping the same water, but basically it means it's pumping less cubic meter of water per unit of energy. So this conversion factor decreases. Here, also marginally here. So but then we combined pump efficiency. I won't go. We also calculated pump efficiency. Of course, pump efficiencies are very low, 0.2 to 0.3 here. Then we looked at what factors can explain this conversion factor other than just the HP of the pump, which I have shown you there. So we looked at the borewell depth, the age of the pump, the groundwater levels that are operating, of course, the aquifer, and there's certain other data we had, service age of the pump, age of the well. I won't go into all those relationships. So these are the two relationships we have used. This is for Anand. So one model we use just using the HP of the pump. Other we combine it with the well depth. And what it shows is like how well these relationships can predict the model observed volumetric abstraction of those pumps. So more or less it works well in Anand. If you add well depth, the relationship improves a lot. But again, well depth data is not something we have easily available. I can have it for 160 farmers, but HP data is something that is widely available across the minor irrigation census. But our relationship works relatively not that well, but still satisfactory. Again, two models were used, HP plus groundwater level. And other than the HP, what we found in Botard is not the HP of the pump. They're kind of using two different type of pumps, submersible pumps and centrifugal pumps. So more than the HP, it was a type of the pump, and the groundwater level played a big role. Whereas you see Anand, I don't have groundwater level here. In Anand, the groundwater level is more or less doesn't vary a lot, so it didn't impact our relationship. Now we use these two relationships to see for this larger set of 160, 180, 200 farmers, we have the electricity data from the utility to see how much water they're abstracting under two different models and whether they're significantly different or not. What we see on an average on Sky farmers, maybe 10% less. But if you want to check whether it's statistically significant, we see because there's a large variance involved here. So those values are not statistically different. So same thing we observe in Anand. In Anand, water abstracting, they're abstracting around 9 times more than the Botard. So in Botard, we have around 350, whereas in Anand, because they're doing paddy, they're selling water, they're doing wheat, they're doing tobacco. So the water abstraction per well is around 3,000 mm. Again, 10% lower in Anand on an average, Sky farmers. But again, the large variance involved makes it statistically insignificant. Again, other than this relationship, of course, we have this relationship between the pump factors. But the other main error we see in specifically coming in Anand, though we have a very good relationship, is that it's difficult how to compare farmer to farmer. You can compare gross abstraction, but when it comes to comparing gross abstraction per unit of farmer, because of this very well developed markets, you don't know for this particular farmer how much area this farmer is irrigating. So we know how much volume this farmer is irrigating, but we don't know how much area this farmer is irrigating. So that becomes another. So if you want, we can compare gross, assume everything is constant, but that's not the case in the field.
He's selling the water as well.
Yes, they're selling the water, and it's not exclusively selling the water to one farmer. This person who's buying this water from this farmer might be buying it from other farmers. We don't know whether the gross irrigated area is 5 hectares or 10 hectares or 15 hectares. We made some assumptions. We had collected data on how much he's selling, the farmer is selling. So again, 10% lower. It's just comparing 1.5 years of data. So we have more data currently going on in the field. Collection is going on. So it has average lower, but statistically insignificant. There are some data errors, data gaps and errors, electricity data also. This relationship might change a little bit, which we are trying to improve. But these are the preliminary results we have from 1.5 years of collection of data. So these are the main conclusion, I think. In the other session, I think my colleague Deepak is also presenting. They have used a different approach, a complementary approach. They have looked at 3 years of energy use data. So what our motivation of converting energy to abstraction was that we said like energy alone can't tell you how much water the farmer is abstracting. Using the same energy, 2 different farmers, they are abstracting they will be abstracting entirely different amount of water. So you can't say their energy use doesn't change or the same energy, they are using same water. So that was the motivation. But again, these results, gross results tell you for the overall thing, whether there has been any change in cropping pattern or some other things, those can additionally change this crop water use of these solar versus non-solar farmers. I think that's it. I'm here whole day, or we can chat up later also. Thank you. And Sundar is here. So I'll just mention Sundar, who's...
Sundar, you would like to say anything?
In the panelist.
Is our partner in this. And,
okay.
So, and thank you very much, Faiz. And what Faiz was telling that for every set of farmers, so that's why even when we have been looking at that kind of a group of farmers having kind of a similar range of the depth variation and the capacity. Otherwise, you can do it only in a clustering, but not kind of as a listing. So otherwise you have to do it for the same class of the pumps and the size and characteristics. So I think there is 1 minute left. So if yes, Ram.
I was just a great presentation. Thank you. And thank you for finally we can see some data on actual water flow in farms. It's amazing. But what I was struck was how is it that when the HP increases, it doesn't really affect the amount of water? Is it because it compensates for the depth pretty much exactly? Like
yes, because that's a aquifer characteristics and the depth. Yeah. Because the one reason for the farmers in some of those Botad areas is because it's going so deeper, they have to have a higher HP pump, otherwise they can't lift even the same amount of water.
But even within Anand.
So yeah, in Anand, so what happens, even if you have a 10 HP or 15 HP pump, so the HP is more. But if your well depth and the screen size is limited, let's say 10 meter, 20 meters, the amount of water that can go into a well is limited not by the HP, but about the screen depth and the well depth. So that's
so the
why
farmers choose the HP to adjust for those characteristics, or is that HP just wasted?
Yeah,
exactly. Wasted. You never know how they are selected. Sometimes
those will not pump the water.
So those wells were drilled, let's say our data says those wells were drilled 30 to 40 years ago. So there has been a lot of change, silting. Maybe they have put 3 screens, 2 screens have gone back. And so that's why it's not very efficient. That's why we can only explain 70% data. So that's cool.
And sometimes, you know, the farmers have a tendency of using the higher SP pump right from the beginning because to take the futuristic scenario into mind. So there are many, because I mean, ideally what we say in engineering and hydrology and hydrogeology, matching of pump characteristic curves with the aquifer characteristic, that I have rarely seen happen. So, I think we'll come back later on. So please keep your questions. We'll be more than happy to talk about that. So the next I invite my colleague Samaranika, and Samaranika will be sharing what we have been doing in Bangladesh, as Faiz was making a point, because here these are more of experimental. We are making a measurements, and there the idea was that you just can't do everywhere the measurements. Can we do at a regional and a wider scale using the modeling? So she'll be talking about our efforts on the modeling. So,
thank you, sir. Very good morning to all of you who are present in this session. I'm Manikanta Mahapatra from MA India. So I'll be presenting on how to assess groundwater sustainability in Bangladesh through modeling scenarios. So as you know, Bangladesh is one of the major groundwater extracting countries in South Asia. And of course, the irrigation is the major share, who takes the major share, and it is 86%. And the irrigation is mostly from groundwater. And over the years, you can see the shallow tubewell irrigated area and deep tubewell irrigated area, they are increasing rapidly over the years. And in the northwest region of the Bangladesh, you can see the irrigation equipments, they are highly equipped with diesel pumps, and the areas irrigated by diesel pumps constitute about 50% of the total irrigated area. So the diesel pumps, they are the major, they are becoming the major share of carbon emission, and they are also contributing to the greenhouse emission and also the climate change impacts. To emit the climate change impacts, solar energy can serve as a clean energy and cost-effective solution for that. However, being the cost-effective solution, people might think that farmers can pump more water and groundwater might deplete. So for that, for this reason, the main policy question was, what is the impact of if we are going to upscale solar irrigation at a higher scale? So what will be the impact on long-term groundwater sustainability? So very few studies are there who have assessed the groundwater sustainability from solar irrigation pumping perspective, and also what is the impact on under future climate change scenario. So we have used regional groundwater modeling for assessing the sustainability. For this northwestern region of Bangladesh, we have chosen because it is the most highly intensively irrigated area in entire Bangladesh. It is the irrigated area here in this region is about 83%, against the 61% national average. And here in this region, 97% of the irrigation water comes from groundwater. So we followed the basic steps, like we carried out literature survey, then collected data, and based upon the literature and data collected, we conceptualized a model. We developed a conceptual model. Then based upon conceptual model, we constructed the model. And after that, after testing the reliability of the model, we went for model prediction under different climate and human-induced scenarios. So coming to model conceptualization, this is the very first and basic step of groundwater modeling. You can see the conceptual. This is the conceptual model of the whole study. So this model, it constitutes total 4 layers. That is 2 aquifers, composite aquifer and lower shallow aquifer, sandwiched between 2 aqueducts. So this aqueduct, upper aqueduct, it is not continuous throughout the area. Its thickness is varies from 0 to 27 meter. And this 27 meter, this more than 20 meter thickness lies in this buried area. This red shaded area you see, this is the buried area, and others are alluvial area. So the total model thickness that varies, that goes down up to 90 meter shallow depth, because we took this depth because most of the pumping for irrigation that happens from this depth only. And we also divided the whole pumping into shallow aquifer and also lower shallow, upper shallow aquifer and also lower shallow aquifer. So the model area is bounded by rivers at 3 sides. At the southern region, it is bounded by Ganges, that is Padma river, and in eastern side, it is bounded by Yamuna, that is Brahmaputra, and in northeastern side, it is bounded by Tista. So these are taken as flux dependent head boundary condition. Head dependent flux boundary condition. And the northwest side, it has been specified as a time varying specified head. We fixed the time varying heads here. So the total model area was 32,000 kilometers square, and the grid model grid size was 1,000 meter. So after the conceptual model, the model was developed in popularly used modular flow model, ModFlow. And it has been subjected to different input data such as river data, then surface elevation, observation well data, then also different sources and sinks such as recharge and discharge pumping rates. So this recharge and pumping rate, they were distributed uniformly over several zones. Finally, the model was calibrated and validated against observed hydraulic heads to fine-tune the model parameters. So as far as model reliability is concerned, model is now well capable of predicting the hydraulic head at several sites, at major sites, with R-square 0.96. And you can see the model can predict the observed trend in a well manner. So after testing the reliability, we went for testing the scenario, simulating the scenario. So we simulated 3 scenarios. So 2 pumping scenarios and 1 climate scenario. Climate scenarios under historical and conventional pumping. What I showed you, that is base model. And for solar irrigation pumping under historical climate data, it is called SIP. And for future climate data, under solar irrigation pumping, it is named as SFC. So I will be presenting the results of both the scenarios, that is solar irrigation pumping under conventional, historical climate data, and also solar irrigation pumping under future climate data. For climate change scenario, as you know, the climate change happens through, like it is visible through changes in rainfall and temperature. So the data goes into model in terms of change in rainfall and temperature, that in terms of change in recharge and pumping. So for so for solar irrigation scenario, solar irrigation pumping scenario, Faiz has presented the results based upon our 1-year field study in Bangladesh. The results have shown that there is not much difference between water application between solar and non-solar sites. So that source scenario, that pumping rate varies between plus minus 10%. So for this, we have tested like plus minus 10 and 30% increase and decrease in gross water application. So coming to pumping impacts of pumping scenarios. Under pumping scenarios, as usual, the general behavior is observed. Like for higher pumping scenarios, during the dry seasons, the water level goes down as compared to other scenarios and base case. And for wet season, when during if this dry season it is the lowest one, then what happens there? Groundwater storage gets increased. That groundwater storage drains quickly, and what happens? Groundwater storage space is created. So during that subsequent monsoon season, the aquifer gets recharged quickly, and it rises rapidly and reaches at a higher level. So this is called Bengal water machine or Ganges water machine. So but however, you can see plus and 10% and 30% pumping increase scenario. There is a general decrease in these boxes, like the hydraulic head gets depleted, and for reduced pumping scenarios, the groundwater head increases. Yeah, 2 more slides. Yeah, coming to cases near the rivers. So these are the rivers. This is Padma river and this is Yamuna river. You can see that during wet season, the high pumping induces higher inflows to the aquifer, which are connected to the river. So also this Yamuna river, because the ground flow direction is from north to south, so there is high recharge inflow into the aquifer compared to this Padma river, because the ground flow direction is from north to south. So there is not much aquifer recharge into the aquifer. So coming to solar irrigation pumping under future climate scenario, I know this is the preliminary results, because we have tested only one model under high emission scenario, and also we have taken 2 pumping scenarios that is most closely pumping, because pumping is within 10 plus minus 10%. So we have considered this plus minus 10%, which is the closest SIP scenarios which was observed in the field. So and also we tested for coming 2 decades up to 2050. So in general, what you see, the mean and median values, they are slightly decreasing. For climate change minus 10%, and for future climate under plus 10% increase scenario. And also second decade is during second decade also, that is also high. But you can see the difference is depletion is higher during the second decade. So with time, the groundwater depletion is increasing. So the key message from this presentation is that with current recharge scenario, the groundwater depletion is higher for the higher water pumping scenarios, and which for the aquifers, those are not directly connected to the river sources, or they have limited recharge conditions like buried area. Then second is high pumping rates induce higher river inflows to the aquifer during wet season, which shows the Bengal water machine. And future impact of groundwater resources is the combined effect of from both SIPs and climate change. However, if that effect is within plus minus 10%, so that is not nothing is going to change. That will be not significant change. So such studies can be carried out, but again, there are many things to be implemented and tested. When many climatic models have to be tested, and under different scenario conditions. For example, yesterday there was a discussion if the aquifers, deeper aquifers are pumped, so what will be the scenario? If shallow aquifers are pumped, what will be the scenario? So such kind of studies can help in developing effective management strategies.
All right, so thank you very much. Still a work in progress. It is only the kind of the preliminary thinking which is gone into that, and of course we'll be putting in more of the more possible futuristic scenarios, and not only the climate change. Our plan is also we are looking into the fact as perhaps yesterday made that presentation that we are also looking into if business as usual and if we change the water management interventions. So all those things are going to be plugged into this thing to get a more holistic thing. So
Manika, I think I have one question. So I've seen the presentation also for the first time. But if you say like if the pumping changes by minus or 10%, then the Bengal even plus 10%, then the Bengal water machine will take care of the depletion. Is that the conclusion from the preliminary study?
Yes, but there is not much difference because plus minus within plus minus difference, there is not much groundwater storage space created. So Bengal water basin will not be that much effective. So for higher pumping rates, it will be more effective because Bengal water basin is what like during the dry season, the groundwater storage space is created and that gets replenished in the during the subsequent months. That is the Bengal water.
Another thing is, well, I think Anwar is whether joined or not, he's having some issue. Yesterday also in his presentation, and also I have seen in Bangladesh when I was there, as he has demystified yesterday also that the Bengal water machine is not going to work everywhere. I think it's very few areas where it has in that paper also shows that it is blocking. But we'll have to see which area we are.
We can use the model to check a threshold at both spatially and also in terms of pumping where it stops benefiting us and goes down.
Okay, so I think let's give a big hand to all the. Before I invite the panel, if anybody has any burning question from any one of those three speakers, because I know this gentleman, I stopped him, so I'll give him a chance, please.
My question is true, sir. You have mentioned that there is no significant difference in water extraction using the TS-20 and 30 SP pumps. And in what time of the year the pumping is done? I mean, only once or more than once? And which season the pumping is done to calculate water extraction from this?
Yeah. That I think, Faz, it is to you.
So we started in August 21. So each pump is tested at least 5 or 6 times. So every couple of months. So we have this across season.
And so one season or throughout the year?
Throughout the year. So we started in August 21. Still the work is going on. Also, the season is only thing you need to consider the season impact on the solar won't impact because these pumps use electricity directly from grid.
So my concern is not for season. I mean, for some of the cases in Nepal, the people demand higher capacities from despite that monsoon season, the pump extract a similar amount of the water, but in the lean season, when the groundwater is go down, in that case, is the higher capacity of the pump could extract the more water. And I was just connecting this in whether there is a possibility that the farmers may demand or using the larger pump to extract more water in water depletion side. That's why I was asking.
So the pump is constant, so you don't change the pump. But the second thing is when the groundwater level goes down, especially in harder aquifers, the flow rate decreases, yield decreases. But not in Anand because the aquifers are good. It doesn't matter in Anand. But in Bhutan, yes, I think that's a similar case as in Anand. We can talk of more.
All right, so thank you very much. I think now as you know that we are hard pressed of time, and now we go next to the panel discussion. So I would like to invite all the panelists to please come over here, and maybe Sundar, if you can pull one of those chairs. Okay, let's see. So I'll invite Anwar. I do not know whether he's still online or not, and Vimal, Dr. Manuel Magombeyi, Professor Abhijit Mukherjee, Abhijit, Alka Subedi from Nepal, Ram Fishman, and my dear friend Sundar Rajan. Sundar, please take your seats. Wherever you feel comfortable, you take the chair. Okay, I can go inside. Okay. Maybe we'll get started, and meanwhile, if he's able to join, then I think we'll get going with that. Okay. And this particular session for the panelists is, based on what has been discussed today in the current session and also yesterday. And I think this is the perhaps last session on in terms of the groundwater and all these kind of things, perhaps in this series of 2 days.
You are more powerful.
You want me to go in the air? All right, I can do that. Yeah, I should face you guys, huh?
Yes, you're the boss.
Oh, no, boss here. Come on. I love it. Like this with you, right?
Okay.
Okay. So, as know that because this particular panelist is more to be talking about the modeling. How can groundwater model help understand farmers' behavior? And of course, one of the attempt was that what Smranika was making a point. And so this is the kind of a thing, but of course, we have shared with you the question because I was asked to put the questions related to modeling, but you can always twist the questions if you don't like the model. So everybody doesn't like the modeling.
Yeah.
I don't know what Ram is looking at me. So
I like them, but I don't understand them.
Okay. So maybe what I'll do is that then let's go ahead with the, I think I'll follow the same order because Anwar Zahid somehow is still trying to link. And so I'll go with the Professor Vimal Mishra. And Vimal, I know, is a great modeler. So, so Vimal, then what do you think is, in your view, the scope of groundwater modeling to understand the groundwater pumping behavior of the farmers?
And this is a very complex, critical question, of course. So as you know, I mean, all models have limitations, and a country like India, where we don't have enough observations to train model other than the large scale groundwater variability data set, probably from GRACE and some CGWB observations. Reaching to farmers' behavior is still a challenge, I would say, but models can help, though models are not perfect. I mean, they are as good as we can make them to understand or answer the questions. We should also sort of have realistic expectations from the model. And first of all, we need to understand what models can tell us, what they have limitations. So that is very, very important, because many times people say that if we can use models, we can answer all kind of questions. And for that, answer is no. So of course, I mean, at large scale or regional scale, or if we have very good data set collected the way IWMI is doing at a well level data set, like what are the pump size and how many hours pump is running, when is running, what kind of crops farmers are using, if we have that detailed data, we can certainly use models to provide or answer questions that how much depletion we can curb by using different practices, by reducing the, let's say, capacity of pump, improving the irrigation efficiency, or replacing X crop with Y crop, because we know the irrigation demands of different crops, right? So these kind of questions we can answer. Of course, we can give a larger perspective, what, like, if this happens, what could happen to the groundwater storage variability, whether some practices are sustainable or not, because we cannot wait until the things happen. So we may not have precise, accurate idea with the modeling experiments, but certainly we can learn that, okay, these are the scenarios which could occur if we go for water intensive crops and the groundwater is depleting and we are providing free electricity, or we are providing solar pumps. So farmers may end up using more groundwater, and then what could be the scenario in next 5 years, 10 years. So those kind of questions. So I would say there is still models fill a big gap in our understanding, but we cannot learn everything. We need observations, and observations are very, very critical in any successful modeling experiment.
Yes, right. I agree with you that, of course, models will give you the general direction and not the absolute value, but the kind of relative way it can give. And also because, what do you think that because the models should not be used per se just for this thing, but more as a tool for in the more futuristic decision making, what kind of intervention should be taken to try and see if this thing is going to happen, how we can take care of that.
Yeah, so sort of consolidating evidences, because we may not have time to run pilot experiment for all sort of ideas we have. So modeling is, if we have reliable, realistic models, probably we can look at the scenarios like we talk about climate change adaptation, and groundwater is a key variable in that direction. So what we should do to sustain groundwater, and what is the best practice, those kind of scenario we can develop and go on field to test it further.
I'll come back to you with more specific question if there is a time that to know, because as you know, these models are mostly at the regional scale. But if we have to do where we are doing experimental measurements, if that cluster of area we have to do any modeling, can we look into, are there any other more granular model that we can look into at more local scale? So just
then I think
I'll come back to you.
My answer would be Ram can help. He develops statistical models, and those can work at point scale.
Well, I'll have a little reservation on that right now. And we will come back to you. So I'll more go for the conceptual model right now. So, okay. So anyway, so thank you very much on that. And the next, I have Professor Abhijit Mukherjee. And I know Professor Abhijit Mukherjee is more into modeling and as well as the field-based observation. So, Abhijit, how do you think that the modeling studies can be employed to study groundwater sustainability under this kind of more futuristic scenarios, like what Samaranika was mentioning, that if this happens, there will be 50% of the area will be converted into solar irrigation pumps and things like that. So, what do you think that is it good enough, and the way the things are being employed, it should be done, or what is your view on that?
Sorry.
More from the ground sustainability point of view.
Okay, sorry. I'd like to start with a more generic statement. Is that okay?
Yeah, sure.
So I'll start with something, with a quote that my teacher, like whom I learned my modeling skills, the legendary Ellen Poiter from USGS and Colorado School of Mines used to say that, all models are wrong.
No, yeah, that is right.
Some are useful.
Yeah.
And they're useful based on the question you ask. Okay. So when you say modeling, like groundwater, that's a very vague word for me.
Yeah.
I mean, there are many types of models. Broadly enough, there are these mass balance models based on
empirical, statistical. We are talking about here the conceptual one.
Well, no, I don't think further than that. Like the mass-based, like conservation of mass and energy-based models. Then you have the fluid dynamics models, like the fields-based models. And then the thermodynamics and kinetic-based geochemical models. Now, when you're talking about sustainability, you have to define what you mean by sustainability, because sustainability has both the physical side as well as the chemical side. So depending on that, you have to define your model, you have to define your questions. Now, going back to what you referred about Swarnika's work, definitely it's possible. And I would differ a little bit than what Vimal said and you said about the regional scale model versus the local scale model. They are achievable. They are achievable as long as you can base the models. You can go for telescopic mesh refinement, define a much broader specified head and head fluxes, and you can zoom in, and then it's achievable. And through that, you can actually predict to a certain extent. Like again, the probability factors would vary from 6 to 20%. You can define how sustainable quantity-wise as well as quality-wise you can predict the future scenarios. So in recent times, like I had, like through my PhD work and more previous work, I've done the physical models. And in recent times, some of my students are doing also the chemical model, like the sustainability of chemical. So we have developed a recent model on Punjab, where we showed that how the climate change scenario might be also influencing the nitrate contamination of groundwater based on the flow systems that are getting, evolving because of more pumping, more climate change, and so on. So yes, it's achievable, but we have to be cautious in the fact that a model outcome is basically a reflection of your conceptual framework. Unless you define your conceptual framework in real sense, your model outcome is just like a hogwash.
Yeah, sure. And I do agree with you when you were telling that, of course, it's the same model can work even at the regional scale and also at the local. But for the local scale, you have to specify the kind of the boundary conditions. And of course, yes, if I have to look at the local scale, I'll have to have more well observation of the preserved data. That's what we are trying to do. Then even the mod flow, you can do it at that local scale. So it's the way you kind of conceptualize it, the way you kind of construct it and implement it. So yeah, so that's pretty much there, and that's what our thinking is in this, that as going forward, we would like to see that if we go on putting various interventions on the management options, like Vimal was telling, that how we can really look into the more futuristic way.
It's all in the scale of observation.
Yeah. And as you said about your professor telling that our models are wrong, even my professor who taught me in Utah State University, a famous soil physicist, when he was doing plant grow and salt grow models, he used a word which I can't use it here. No, don't do that. He wrote it in the board. Keep it simple, stupid.
Yeah, kiss.
Kiss. And he said kiss, then everybody was looking at him, and then he said keep it simple, stupid.
Silly or
stupid. That look, don't be always so mathematically correct and everything. You have one foot fit in the field and one in the lab. So just don't be only so that's what we are trying to see. You see, there are colleagues, we are trying to see a mix of both. So I see that Dr. Anwar Zahid is joined. Anwar, you are there online?
Yeah, I am here, and good afternoon, everyone.
Good afternoon, good afternoon. So we were just started with Professor Vimal Mishra and your good old friend Abhijit. And so we are talking about that. So maybe, what do you think? Because, you must have been listening to them when we are trying to look into the groundwater modeling, particularly looking into the farmers pumping behavior and trying to see how under the various futuristic scenarios, the groundwater sustainability is going to look like, particularly if there is a future expansion of solar irrigation at a scale. So what do you think are the key challenges in groundwater modeling to understand the groundwater sustainability issues or the farmers pumping behavior, and what could be the better ways to handle that in the future? Over to you, Anwar.
Okay, thank you. I am sorry, due to a connection problem, I was not able to listen the previous.
Maybe right now also, if maybe you can maybe switch off your video. Otherwise, then I think that I know. Yes, please.
Okay,
photo is looking good. That's what Abhijit is complimenting your photo.
Thank you. So what I was saying that I was unable to listen the previous presentations. However, you have a specific question. Obviously, modeling is a very important tool to understand the mechanism. But here the limitation is if we do not know exact field situation regarding abstraction and also the recharge mechanism, then model may misguide us. Okay, if we consider the Bangladesh perspective, in general, we have data. For example, we have irrigation well inventory data, so we can estimate the abstraction, and also as we monitor groundwater table throughout the year, we can also go for estimation of groundwater recharge. Okay. So, but the problem is that our hydrogeological system is very complex. Our hydrogeology is very complex. Though we have data, but we do not actually know what is going on in between. Our lithologic stratification also varies very much within even small distances. So only with the modeling, with the very scarce data, it is difficult to assess the present condition. And if the present condition is not what I say acceptably assessed, then we may get the wrong information. So okay, now we can use for example what it say we use nowadays to cover the data gap nowadays intelligence of machine learning. So machine learning, yeah, we have also data regarding, for example, hydraulic conductivity and so on. So if we have such reliable data, then model obviously a good rule. And with the model, if what I have mentioned, with the machine learning process, if we consider the hydrogeologic condition during development of model, we may get more accurate data. But model is obviously an important tool.
No, thank you very much. Also bringing in the point of machine learning. Of course, that is something that can also be food for the thought for the future. And definitely, and as you very rightly mentioned, it's not the model, because the same model can be used as a tool by somebody in a very wrong manner, and the others can use it very precisely. So that is, of course, the major art of, or the skill of using the model, because the same model is used as a good amount of tool by some and not by others. So that's, of course, has to be, that's what we are trying to be looking into that. So, okay. So I have now two more panelists, three rather. So Alka from Nepal. So Alka, because I know you said that you don't like modeling.
No, I
so,
didn't say that.
so my question to you is
Yes.
that what do you think are the other potential ways and the means to look into this or understand farmers pumping behavior other than groundwater modeling, which we are talking about?
Okay, so thank you for the question. And regarding the modeling, groundwater modeling, as we said that, as we have been discussing, that it needs a lot of data and it needs to be really precise in order to get this data. But in case of Nepal, if I have to talk precisely for Nepal, we don't have too much information regarding the hydrogeological conditions of the country, because we have a different physiographic differences in the landforms. So maybe for us, the better way or the simpler way, if I have to put it in that way, the or in the region or in this region also, the simple way could be the metering of the groundwater pumping.
Like
yes. So if you can see the amount of water that is being extracted, like we do for the water supply. So if you meter the groundwater pumping, then you can know the extraction rate. And the other thing can be you can also look into the events that are occurring, that the rainfall or the runoff in the river. So you can know the groundwater discharge that is occurring in the region. You can also look into that aspect. And the other is you can, other way to monitor the groundwater could be the pump uses. Because if you use the water uses and the pump uses, both if you can validate that or you can keep record of that, this can also help to understand the groundwater condition in the region rather than going But as we say that the groundwater modelings are more precise than this kind of readings, but this simpler way can also help you understand the groundwater condition and the recharge condition.
Thank you. So you validate what Faiz is doing,
yes.
In a way. Right.
Yes.
So anyway, my next panelist, I'm sorry, I have to run it faster. So Ram.
You can skip over me.
No.
I'm very intimidated by the subject.
I give you a choice for your own question, but anyway, I'll not give you a choice. Let me ask you, because you are a modeler. So, which model? I'm not telling mod flow or other thing. Any kind of a conceptual model, empirical model, statistical model, stochastic model, which models would you suggest for such a studies at local or regional or both the scales?
To be honest with you, you guys are all hydrologists complaining about your models, but you think, you should be very happy because if you went into social science, you would see that you're actually in a good shape. Our social science models are, I won't use another word that you can't say here. They're very, very, very limited. The explanatory power is absolutely pathetic. So it's hard to predict farmers' behavior. So on the behavior side, our modeling is very, very poor. We usually are able to predict very little. So I'm kind of jealous of you guys that your models actually, I saw the fit in your modeling was very impressive. And
so I put it in a different way now.
Okay.
The same thing, bringing like suppose this hardcore modeling, but do you think just going this modeling is enough, or we should bring the social component added to that, like what we call now the socio-hydrology or agent-based modeling, or we try and bring some of those things to integrate it together with this our hardcore modeling?
So I come from like a school of thought in social science that is a little bit, all these, like you said, keep it simple, stupid. So these models would be great if we knew, like in agent-based modeling, if we knew how to characterize the simple decisions made by each individual farmers, we could aggregate them beautifully with agent-based modeling. And the problem is we don't have the foundation. Like you guys know, when a molecule of water, there's certain parameters that the velocity of flow will be that. But in the behavior side, we don't have the basic rules of behavior. So I think we have to be careful not to go into these complicated, like, other systems that it will look really amazing when it will look impressive, but it's a little bit of the foundation is not there. We don't have the basic rules of behavior in most cases. So I think that's an issue. But one thing maybe where I can say something more constructive and not just complain is that I wonder if there's a way to generate more data for the purpose of groundwater modeling. This is like the first time I ever see data on water flow and water application. I think it's amazing that you are doing this work, and it just has to be, there has to be more of that. We have to find ways. We should find ways of making it less expensive to know, like, we know every day how much rainfall falls in every location, and this we measure 4 times a year. We get a monitoring point for the depth of the water. There's got to be ways to make that cheaper in our day and age and more scalable.
All right. So fairly good enough. I appreciate your points. And now my last but the most important for the session, Sundar. Sundar is also part of our this thing. And Sundar, like we have been listening to both the sides, hardcore modeling and the experiment. But as you know, my view is that both have to be meshed together. Either or doesn't work. So you being earlier a modeler and a good analyst, a groundwater hydrologist, and now so much grounded in the field, how do you think that we can learn both of these things in a way that we get near real life situation?
Yes, sir. Look, I think one of the statements earlier person made, no model is also a model.
Yeah.
Right. I mean, sometimes we just say that these mod flows and everything we don't want to get into it because there are too many parameters in it. But then somewhere we have a picture in our mind, right? When we make an estimate, and that's also a model. We have some kind of a picture always. So there is very old, when these people started numerical modeling in the 60s, Freeze and others. So first, if you remember, there was this Stanford parametric model, right? It started with 25, 27 parameters, 64 parameters. So there is this early concept in modeling. I think we should revisit. We don't know, we should, if it is really a principle, but it's called the parsimony principle.
Yeah.
Right? Basically, it says the least parametric model that can actually do your job with reasonable uncertainty. And as Abhijit also spoke, what is your job, right? What is it that you really want? For example, in our case, we are trying to say a big picture estimate. Hi, Anwar, after long, seeing you. A big picture estimate of what is the groundwater picture of Gujarat, let us say, with solar or without solar. That's a large question that we're asking. So if that is there, what I think I find interesting with these kind of approaches is that you're looking at the simplest model, which has few parameters, but then there is some estimate of uncertainty built into it. So over here, okay, we have just two locations here, alluvial or a hard rock. There are so many possible, scenarios. But then how do you really build, an estimate of uncertainty inherently? But there's also an external understanding of uncertainty, which you need to bring in. So something interesting which I found today, which I had not noticed earlier, is that in this case, when we presented Anand in Bhutan, the largest volume of water is Anand, right? And normally you would assume that the larger errors and uncertainty is with that side of the model, which is dealing with the large numbers. But what you saw here was actually the reverse. You're getting greater errors into the smaller side because of totally different reasons, because of geological heterogeneity in the hard rock side. So sometimes certain modeling approaches could actually work in the large scale, because now I think it gives us hope, because the large numbers are about these alluvial aquifers. If you look at the large scale, so then the errors probably, with other assumptions, the error probably, would be less magnified. So my take is that, even when I practice, I keep looking at simpler models, but then it is also a slippery path, to go down, slippery, but not to put down more data driven. But end of the day, if you can do ground truthing as we are doing it here, and you can do ground truthing over time, then it hardly matters what model you have. I mean, that is the whole digital twin approach, which is picking up from computer animation, graphics, and other spaces where there is a data rich experience. It doesn't matter whether machine learning or whatever you have, as long as data rich, then you have a digital twin which mimics the real world. So more data, how can you make data collection cheaper? Then any model is fine.
All right, so thank you very much. And I know there are many things. I think we should have sometimes in the future exclusively half a day session on this to discuss, because these are very important things. And I like your statement of no model is also a good model. Yeah. So that is something I think is good takeaway. And also, as you mentioned, yes, I mean, we would like to see that we keep it simple, stupid, and but at the same time the rigor, because we have a conceptual rigor and with the parsimony of parameters, because that parsimony of parameters is very important. And even those who are hardcore models, they also would know that in a model there may be 64 or 32 parameters, but if you really run the sensitivity analysis, you will try and see maybe only 2 or 3 or 4 at the most, so critical. So sometimes we end up even looking into those kind of things. So anyway, time is short, so thank you all very much. But Vimal is raising his hand, so
yeah. So just wanted to add, like, there are many people among us who may not like physics-based models, process-based models that we call, but they are very, attracted towards machine learning models. And there is a disclaimer, or there is a notion of this caution that machine learning models even require more data.
And that's more
then the process, then process-based model. So if you don't have data, a machine learning model may be even worse than the process-based model, and we have to be careful in using machine learning.
Machine learning is basically it's big data, and you are using it like a training data set. It's more like a pattern recognition.
Exactly.
So that's what it is. So I think we leave this at a very positive note. That yes, I mean, it will be good to have how best we can integrate our experimental observations with the hardcore modeling and try to see that we
like a magic.
Have a balance of both and don't lose the feel of the ground reality. So thank you all very much. Thank you all the panelists and thank you all the I'm sure